Hello JuliaCon, my name is Carsten Bauer, and in the next 30-ish minutes I will show you how you can monitor the performance of a piece of Julia code on a hardware level with a LIKWID.jl. The promise of my talk is that by the end of the talk you have understood how for a generic Julia function computation called here, you can count, for example, the number of floating point operations that have been actually conducted by the CPU. And equally, you will be able to do the same thing on the GPU. My talk will be structured as follows. First, I will say a few words about hardware performance counters and LIKWID, that is the tool that we build upon. LIKWID.jl, that is the Julia wrapper that I wrote. And lastly, I will showcase a few examples that show you how a LIKWID.jl could be helpful for both teaching but also production use cases. Hardware performance counters. So how do we actually benchmark or monitor the performance of Julia code on a hardware level? And the good news is that there are counters built inside of most modern CPUs, which can measure all kinds of things: instruction statistics, branch mispredictions, cache misses, floating point operations, all kinds of interesting things that you might want to analyze when analyzing your code. However, to actually use these counters, right, you actually most of the time need an abstraction layer, because accurately using them directly is very difficult. Not only do you have to find a way to actually access them, but also they are typically sparsely documented. Types and meanings of counters can vary between CPU generations and even more so between architectures. And they can have annoying bugs, like miscounting and so on. So you want a trusted, tested intermediate layer. And that brings me to LIKWID, which is exactly that. So LIKWID, which stands for Like I Knew What I'm Doing, is a collection of tools developed and maintained by the National High Performance Computing Center in Erlangen in Germany. And again, it's a collection of tools for performance monitoring, thread pinning, micro benchmarks, frequency tuning, all kinds of things. And in this talk, I will focus on the performance monitoring aspect only. So again, why LIKWID? Because it's this well-tested abstraction layer that makes hardware performance counters, in a way, actually usable. In particular, LIKWID will, instead of just the raw counter events, which can be cryptic to analyze, provide you with derived metrics. So, meaningful things that you can interpret right away. In particular, you will be able to specify a performance group like flops DP, where DP stands for double precision, which will then give you, interesting information about double precision operations that your Julia code has performed. Equally, you could choose MEM or L2. There's a bunch of those. For example, MEM and L2 are related to measuring the memory bandwidth or the L2 cache bandwidth. LIKWID.jl is now a Julia wrapper around LIKWID, and I've developed that in collaboration actually with the Erlangen people, so the main developers of LIKWID. So at that point, I want to acknowledge Thomas Gruber, which helped me a lot with getting LIKWID.jl into the state it currently is in. Thanks also go out to David Barrera for the nice logo which he created, and also Valentin Shurabi for kicking off LIKWID.jl in the first place. And again, the rest of the talk will be about LIKWID.jl. And first, I want to talk about the installation. While installing LIKWID.jl is very easy, it's the typical using pkg add liquid, or whatever other option there is around. Currently, we don't ship automatically the underlying LIKWID binary. There is a work in progress, PR for Yggdrasil, which will provide that as a Julia artifact. But for now, you have to compile LIKWID from source. Fortunately, typically this is not too hard. So the only thing you have to do is you download an unpack LIKWID. As of recording this, the newest version was 5.2.1. You can use the link that I show here. Then potentially you modify the config mk. I'll talk about this more in a second. And then it's just a make and make install. And by the way, at that point you might wonder, make install, this all sounds like Linux, and that's a big disclaimer I have to make. All of this is only going to work on Linux. So in principle, it's just these 3 steps: downloading, modifying, make install. However, there's one important thing that I want to talk about, and that is access modes. So Liquid will access these counters inside of the GPU, inside the CPU or GPU for you, and there are different ways of doing that. One is direct, another one is access, like an access daemon. Both require root for the installation and are perfectly fine if you install them on your local machine. However, when you work on a cluster, you certainly won't have direct access to the performance counters, and most likely the HPC staff also isn't happy to hear about your request of wanting an access daemon running in the background with root privileges. So in that regard, the path-end event is the one that, despite the fact that it not provides all the features that Liquid is capable of delivering, it doesn't require root. So this is typically what you should go with if you don't have root privileges. So let me be very concrete here. If you want to install Liquid, essentially you change 2 things. You change, like without root privileges. So you change the prefix from the generic Unix system resources local to a path in your home directory, for example .local, and then you choose the access daemon to perf event. And optionally, if you also want to use the NVIDIA interface, you change that switch in the bottom to true as well. All right. Assuming that you manage to install Liquid, and again LIKWID.jl, which is trivial, we can actually now turn to measuring things. Performance monitoring, that's the main focus of this talk, and it lives in the perfmon module within LIKWID.jl. Let me show you how you can utilize this tool for actually benchmarking something. The example I want to focus on is xpi, which stands for a times x plus y, where a is a scalar and x and y are vectors. So a very straightforward operation, which is built in every BLAS. And here we focus on, at least for now, float 64 double precision. So on the right, I show a regular Julia code, like some draft implementation of an xpi, multi-threaded, and should be straightforward to understand, I hope. And if you want to measure now on a hardware level the performance of this xpi function, and let's say we care about the floating point performance, the only thing we have to do is we wrap the function call xpi in this little macro at perfmon. We provide the performance group, which I mentioned earlier. By the way, you can get a list of all of those with perfmon supported groups. And then eventually it will run our code, again, monitor these counters within the CPU, and then return metrics and events, variables that will store the derived metrics and the raw events returned by Liquid. How does this look? So if you actually execute this, apart from these return values, which you could use to programmatically process the results, you will also get this nice visualization from which, for example, if you look at the very bottom, you can conclude that all the threads approximately had the same performance, that is the same megaflops per second. So I hope this is a very easy and straightforward way to benchmarking, for example, a certain function or a certain block of code in Julia. However, very often you want to not measure just an entire function. Imagine that this function would be a large simulation or something like a large a larger computation. Oftentimes you only want to benchmark a certain piece of it. And this brings me to the next topic, which is the marker API. So as the name suggests, the marker API will allow you to mark pieces of Julia code and then only benchmark those. And the way to do this is, again, here is our xpi example in a slightly different formulation without multi-threading, for example. And the way to use the marker API is very straightforward. You just put a marker in it somewhere, a marker close at the end, and then wrap the part that you actually want to monitor into this add marker macro. And here, this xpi is just a label which will, can be used later to identify that particular section. You might have many of those, right? In that example, it's unnecessary, of course. And crucially, once you've augmented your code like this, you can now run your Julia code under a little command line tool, which you've gotten by and from installing Liquid, and that is liquid perf counter, like liquid minus perf counter. And the entire call that you have to make in most cases looks like this. And let me dissect this because it's quite a beast. The first part, Julia underscore exclusive equals 1, is very important. And what this does, it basically sets the thread affinity of our Julia threads. So it pins the Julia threads to the first n CPU threads, like hardware threads or cores for the sake of argument. This is critically important because, again, Liquid will measure counters within a CPU, like for a particular CPU core. And if your Julia thread is running on a different core, then obviously you will get nonsense results. So thread pinning is very crucial when doing anything with Liquid. So Julia exclusive equals 1 takes care of that. If you need more fine-grained control, you can use a package like threadpinning.jl, a command line tool like NumaCTL or other tools out there. The second part is this -c argument, for which you provide the number of like the IDs of the CPU threads, that is the cores that you actually want to monitor. So essentially that should, not just essentially, this should really match the cores where you pinned your threads to. So as I said, Julia exclusive pins to the CPUs, the first n CPU threads, and they start with 0. So we here you would provide 0 minus n, where this minus indicates a range. -g is the argument where you can provide the performance group, as we did to the macro earlier. So here you could, for example, write flops dp for double precision floating point statistics. And again, you can get an entire group of these with perfmon supported groups. Finally, you need -m to turn on the micro API, and then after all this mess comes your regular Julia code. So just Julia -- project -t, whatever, your code. And if you run this, again, for this example that I showed on the previous slide, you will get an output like that. So it's very similar to what we've seen on the Julia side. However, now it's only for a certain region. So in the top, you can see region xpi. So it's only that part that has been measured. For example, loading packages or things like that is not part of the statistics. And then, you get floating point statistics as earlier. Let me now come to GPUs. So all of what I've said before, so at perfmon for monitoring, interactively within a Julia session, monitoring the performance on a hardware level, and also the marker API, both also works on NVIDIA GPUs. The only thing you have to keep in mind is that perfmon now becomes at nvmon for NVIDIA monitoring. So on the right, again, our xpi implementation. However, this time a very simple CUDA implementation, like running on NVIDIA GPU, where we utilize the high-level abstraction features of CUDA.jl. So basically, we just initialize our x and y and z arrays as CUDA arrays. By the way, that defaults to float 32, so which is why I also set a to a float 32 literal here. And then we just broadcast, which, again, by the magic of Timbasar and CUDA.jl will then run efficiently on a GPU. And again, to monitor the performance, we wrap all of this into this at nvmon macro, same thing as before, and then, just have our regular function call. And if you do this, then you might get an output like that. It's a bit less information because, the NVIDIA doesn't spit out as many informations for us, but we can still see the number of, conducted flops, the performance, the megaflop per second, and so on. Again, let me also show the marker API in the GPU case. So the only thing that changes here is that marker becomes GPU marker in both the macro and also the module name for init and close. And looking again at how you have to run your Julia code for that to work, the liquid perf counter call now looks like this. It's a bit shorter because we don't have to pin any threads. So again, let me go through these two pieces that I indicated by color here. So in yellow, similar to the CPU case, you have to provide the IDs of the GPU. 0 means the first, and then you can again use 0 minus n to indicate a bunch of them if you have a multi-GPU application. And in green, with minus W, you provide the performance group. Again, something like flops SP for single precision flops or data. And you can use nvmon.supported groups within Julia to get a list of what is supported on for your particular GPU. Again, you need this minus M to turn on the marker API, and then your regular Julia call, Julia -- project, and so on. If you run this, you might see an output like this. Again, very similar to what we've seen before. The numbers are a bit higher here because I think I switched from 10,000 to something like 100 million or whatever, or 10 million for the vector length. So that's why these numbers are higher, but it's very similar. And again, you could have multiple of those regions within a bigger code, and then only benchmarks specific cases. All right, that brings me to showcasing. So by now you have already learned all the tools and seen all the tools that you need to actually implement the example from the start, which is this reactive performance monitoring, this reactive counting of flops. So how does this work and what do we do here, right? So we define a vector x, which has a certain length, and an arbitrary computation which operates on x. In that case, it performs one flop per each element of x, so that means 10,000 flops. How do we actually measure this with Liquid? Well, we load Liquid, we wrap it in the add_perf_mon macro, and then eventually read off the respective values from the metrics. So what I do here is I read off from the flops DP category, and the first thread, there's only one here, but nonetheless I have to provide the one, the double precision megaflop per second information, and then multiply this by the runtime to get the megaflops. And this is then what is spit out as counted flops in the top. And I think this is a very cool example, not just because you are capable of monitoring. Like now, if I change this function, right, the number of counted flops changes. I think that's super cool. Again, this is measured on a hardware level and not done by some, let's say, macro shenanigans where I look out for plus and multiply operators. However, getting back to my point, I believe this is a cool example, not just for the feature itself that you are capable of counting flops, but also because it combines this high-level interactivity, this reactivity of Pluto.jl. Check it out if you don't know what it is. And LIKWID.jl, which in the past has only been a very low-level HPC-like tool, right? So I believe this is a cool example for what interactive high-performance computing and performance engineering can look like in Julia. I hope you find it as cool as I do. Another example, which I won't go into as much detail, is reactive performance monitoring in a sense of creating an empirical roofline model. So what is a roofline model? The roofline model is a very simple performance model, which essentially always looks like the plot on the right. So you have that black line, which is the roof line, which indicates in one way or another the maximal achievable double precision performance of your system. So in the left region where you have the slope, this is the memory bound region where memory bandwidth is what limits your computation. On the right, it's compute bound. So this is like the absolute peak flops that your system can achieve. And the x-axis, which varies between those two limits, is the operational intensity, which essentially is just flops over bytes. So if you have a kernel, right, it might perform some floating point operations, and at the same time, it might transfer some bytes for example, because it accesses some arrays or similar and has to read that data from memory. And the operational intensity is then the ratio of those two things. And that puts you either in the memory bound regime or in the floating operation, like in the compute bound regime. And what I show here is, I don't show this as an interactive example. I'll put this up in the Liquid documentation soon. On the left, you just define some generic Julia functions, right? Some similar to the computation we had on the previous slide. One is multi-threaded, the other one is not. And then you can use Liquid to measure on a hardware level the number of bytes that have been transferred, the floating point operations that have been conducted, and then just empirically or numerically create that point and put it in that plot. Typically, people do this analytically, so they estimate by looking at the code how many loads there are, how many stores, and so on. So Liquid can be a cool tool and helper here, I believe. All right, that's as much as I wanted to say about the roofline model. Let's come to a third little demonstration of how I used Liquid in the past, and that is write allocate. So when writing a package called bandwidth benchmark, which essentially is just a tool for performing a benchmark of your a measurement of your memory bandwidth. So it's a tool to determine the maximal memory bandwidth on a system. And the way this is done is you implement these streaming kernels. So these kernels, like shown in the top, the Schönauer triad, which is very memory bound, and just because it's very few flops, right? Just one plus and one multiply. However, it's many reads from arrays and stores to A and so on. And by measuring, the speed, so bandwidth benchmark actually makes a timing measurement of this thing, and that concludes from that, what the memory bandwidth must have been. Anyways, given this Schönauer triad shown here, the naive expectation, if you look at that code, you would think that there are three loads, right? So memory loads, if you will, right? So for B, C, and D, we definitely need to load the ith element to be able to perform that computation. And then, there's one store because we want to write into A. However, in reality, many systems do a so-called write allocate, which means that A needs to be loaded before you can store to it. So there's one extra load that is, perhaps not intuitive or not clear if you have never heard of a write allocate before. And so now you might be skeptical and say, well, I don't believe you. I don't think that's actually what is going on. And the nice thing is we can use something like Liquid to prove that that's actually the case. I mean, it's not a literal proof, of course, but you get the idea. And the way I do this is I just, again, monitor that particular kernel. I augment my bandwidth benchmark code with the marker API. I benchmark only that particular piece. And then I look at the memory that has been, went over the memory bus, that has been read and written. And if you take the ratio of those two numbers, you will find that there are 4 times more reads than writes. And that is exactly, that ratio between these 4 loads and that one store. And I think, this is you see here the potential of Liquid to do some very, intimate analysis of some computational kernels. All right. So that, essentially concludes my talk. If you like LIKWID.jl or HPC computing with Julia in general, feel free to reach out to me. I would like to see more users. Feel free to file bug reports as always, right? And since I have, a little time left, let me actually not stop here, but do a small self-advertisement, just a tiny bit. And that is, let me give you a small list of some Julia package that we develop at PC Squared, like that is the Paderborn Center for Parallel Computing. And I just want to pitch them here. So we try to expand, the Julia HPC ecosystem in that regard. So thread pinning, I mentioned it earlier. It's a very cool tool which allows you to dynamically pin Julia threads to CPU threads. Stream benchmark, bandwidth benchmark, cousins, which both allow you to, measure the memory bandwidth of your system. LIKWID.jl, obviously the main player of this talk, and also GPU Inspector, which allows you to benchmark the maximal GPU performance, perform stress tests where let your GPU glow for a certain amount of time, and then monitor, for example, the temperature and power. If you wonder why this is useful, we use this to assess GPU nodes in a newly acquired cluster at our HPC center. Anyways, small advertisement section. Feel free to check those out and get in touch if you're interested in those. And that actually now concludes my talk. Thank you for listening, and see you guys around in the Julia Slack or on Discourse.